Good evening, everybody. I'm glad you're here. I'm glad I'm here. I'm glad I'm anywhere. This is the Great Minds program, as you know, and today we have an absolutely wonderful opportunity to learn something. Our speaker, Roald Hoffman, professor at someplace in Cornell. I've got that down. You know, introducing a great mind is always an awesome obligation, especially this great mind. How do you caricature someone who won all the prizes that the American Chemical Society gives? And the American Chemical Society gives lots of prizes. He has them all. I don't know whether he puts them on at night in his pajamas, and but I bet it would take him an hour at least. His scientific achievements have made him one of the most internationally renowned chemists of our time. A chemist who has published over 500 scientific articles, several books on chemistry, who has been awarded over 30 honorary doctorates. Oh yeah, somewhere in this plethora of awards, certificates, medals, recognitions, there is a Nobel Prize in Chemistry, which was given to him in 1981. His scientific research included a task, this is interesting, of teaching his colleagues in chemistry the power and the simplicity of solid-state physics. And then, even more difficult according to him, teaching physicists the chemical way of thinking. However, because of his major legacy actually, although these were two teaching obligations, his third teaching obligation was teaching to the general public the role played by science in the present-day world. Probably no other contemporary scientist with his awesome scientific reputation and productivity has devoted so much time and energy to advancing public understanding of the role of science in today's complicated world. I would damage the brevity of any introduction, but I should also say one more thing about our speaker today. He has authored something like 5 books of poetry, essays, literary journals, newspapers, and has been the author of 2 plays. And I think that's enough of an introduction. So without any more ado, I'll introduce Dr. Roald Hoffman.
Thank you, Leon. It's a pleasure to be here. I want to tell you 3 views of chemistry, and then something about the essential tensions will come out. So, there was chemistry before there were chemists. It was called various things, but this is the first definition of chemistry, has been there for millennia. And this is that chemistry is the art, craft, and business of substances and their transformations. Things and things changing. We have been put on earth to change it. The origins of everything we have are natural, and we transform it. Now, the reason this definition was there, because people did things. They cooked, they made, they won metals from their ores, they made soap, cosmetics, medicines, all these things were done before. Let me just give you an example. Here is, for instance, at the top 3 works of art from various civilizations, all old. a wall painting from Luxor in Thebes, 4,000 years old. On the left, in the middle, the Gate of Ishtar, once stood in Babylon, then through a feat of imperialism, for a change not American, but German, found its way to Berlin. And at right you see a period of art of realistic representation. This is a Hellenistic wall painting which preceded the Italian Renaissance by 1,500 years. The Dark Ages really were dark. People painted like that around the time of Christ. The blue or green in these paintings is not the natural pigment that has always been available if you had the money to buy it, and that is powdered lapis lazuli or ultramarine. The blue or green in these is a product of human manufacture, which was a commercial item of chemistry among the Egyptians, comes from the Egyptian manufacture of glass and enamel, which they were masters of. And when you add to the ingredients of glass, it's essentially a glass, which means it's silica and sodium carbonate or natron, which was available to the Egyptians, and high temperatures. And when you add to that a little bit of a copper pigment, you get this blue color. Here it is in a powdered form. This is Egyptian blue, and there is a molecular structure of it shown in atomic detail. So this is chemistry. This was chemistry. People did this. They got skilled at it through experimentation, not through any theory, and passed it down within families, within tribes for generations, and mastered the craft and for profit, for benefit a long time ago. Now, in order to show you that in another way, I really need to show chemistry as substances and their transformations, because the transformations is not obvious here. That is how this was made. I told you how it was made, but it doesn't have that feeling unless you make it. In order to do that, I have to do a chemical experiment, and I didn't know whether the safety committee of this auditorium would allow me to blow anything up here. And so I have some slides. So here are two substances. Things. In this case, two elements. At left, reddish-brown liquid with a gas above it of the same color, bromine. At right, aluminum, a metal. Neither of these was available 300 years ago. They were first actually made just about 200 years ago for the first time. And they're an interesting story about them. Aluminum, Napoleon III served his best dinner guests on a service of aluminum. The second-rate guests got gold. And the tip of the Washington Monument, when it was built, was out of aluminum. Within 5 years of the building of the Washington Monument, a young man in Ohio, sorry, wrong state, and 23 years old, and another young man, quite independent in France, Hall and Heroult, invented a process for making aluminum as cheap as it is today. It wasn't so cheap. You put one into the other, you get flames, heat, foul odors, absolutely everything you expected of chemistry. And at the end of it is something else, which is an aluminum bromide, a complicated one. Okay, this is chemistry. Now you see substances and their transformations. And this was chemistry. This always will be chemistry. And to this day, smokes, foul explosions, flames, foul odors, and colors are still what attracts people to chemistry. If you want to read about this by someone who's outside of the profession to testify to this, there's a wonderful biographical memoir by Oliver Sacks called Uncle Tungsten's Memories of a Chemical Boyhood, which tells the excitement that a young person growing up in England, in this case, around World War II, would feel on going through this chemistry. There are some consequences of this definition, and this will lead eventually into the third definition that I will talk about, which is the perceptions that we have of chemistry. But one consequence of this fundamental definition, that chemistry is deeply and fundamentally about change, not necessarily explosive change, sometimes slow change, but still about change. One consequence of this is this, which I flashed on before. This is a 1942 Donald Duck comic book. One of the early members of the Walt Disney stable, Carl Barks, drew the whole comic book and wrote the story. Today, 200 people would be required to do that with computers, but he did it all himself. Here is the first page. You can't read it exactly, but it doesn't matter. Certain canonical things transpire in Donald Duck comic strips. The nephews are playing, doing something innocent. Donald Duck comes in, he does something stupid. There is an explosion, and there is inevitable egg upon the head. This is the rough storyline of every Donald Duck comic strip. And that is what happens here. What's interesting at the bottom there at the right is you can't read it, but they're slightly misspelled as some chemistry. My colleagues are complaining there isn't enough chemistry before the general public. The most interesting thing, which is why I've made it larger, is the next panel in this book. And Donald Duck says, if I mix CH2 with NH4 and boil the atoms in osmotic fog, I should get speckled nitrogen. And the nephews answer appropriately. The point, why is this interesting? Because this experiment has not been done to this day. And if you are a chemist, you might know why it's difficult to react CH2 with neutral NH4. But I will not talk about that. But why do I show this to you? The one reason, of course, is this is fun. That's clear. But the other reason is that what you see here is part of the forming image of chemistry in the general public, which is there inevitably and cannot be escaped, that chemists are the people who make things go bang, okay? Summarized in one sentence. And that is something that we have to live with, even though some of the reactions, even though the reactions that go bang, you can be sure are not the ones that are used by the chemical industry. Making things go bang is pretty wasteful. So that transformations are controlled, but in some way they still are. What goes on in your internal combustion engine, there is no tiger in there, but indeed there is a flame in there, as action movies show. That flame is well hidden in a normal engine, but it's there. It's burning in some way. There is another story that connected up, actually, to something with Wendy Doniger was here, talked about. This is another consequence of that basic transformative nature of chemistry. When there arose in cultures across the world, in India, which is why I mention her name, and I'll come back to her in just a moment, and in Egypt, in China, in Greece, when there arose 2,000 years ago, philosophies of transformation which were competing in some way or in some way in trouble with the religious frameworks that were around them, but which took part in the power of those philosophical frameworks. I'm talking about alchemy. Took part of the same myths that power those religious frameworks. And let me just, and this is why Wendy and I agree on things very much. In my vocabulary, myth is just about the best word possible. It is not a negative word. what myths am I talking about? These were philosophies of transformation. What kind of transformation? Of course, desired transformation of a sick person into a healthy one, of a poor person into a rich one. A desired transformation. Now, what kind of myths were behind these things? These are the greatest myths of them all. Phoenix rising from the ashes, Persephone returning from the dead, reincarnation, the greatest myth of them all, the resurrection. These are the myths that power civilizations and religions. When there arose philosophies of that, which were always in trouble with the religion surrounding them, and those philosophies of transformation, they were secretive, hermetic, and they needed a logo, something to get into people's minds with, something which represented in people's minds transformation. They chose what already was in people's experience around them that was transformative, that you could do in a demonstration, and that was chemistry. So you heated mercury, very high temperature, and it formed an orange crust on it. And you heated that again, and the orange crust decomposed back to the mercury. That's transformation. The chemistry of mercury, arsenic, antimony was particularly rich of sulfur in transformative aspects. Here's a typical alchemical painting, late representation. Alchemy lent itself for very good reasons to artistic representation. You see here, this is very typical. In the background there is a king and a queen getting married by a bishop, and in front are people doing chemistry. Now, I grew up in the 60s, 50s, and 60s. I went to quite a few hippie weddings in California in the early 60s. There was some chemistry done at those weddings, but not this kind of chemistry that you see here. So what is going on here? This is not the real world. This is the symbolic world. The chemistry in front, real, both are real. The wedding in the background and the chemistry in front, but one is a symbol for the other. The chemistry in front is the union of the elements of compounds, and there is something going to happen in the background. And both are generative in the sense of creating something new. A very interesting thing. This is not your typical view of alchemy. The typical view of alchemy is that alchemy was pseudoscience. A little more sophisticated view of alchemy, or a realistic view of how modern chemists think about alchemy, is that they take what the alchemists got for us, because the alchemists did do experiments for us, and for instance they made the strong mineral acids, hydrochloric, nitric, and sulfuric, for the first time in the Middle Ages in Europe, and they learned how to dissolve gold. And these, we take the chemistry. You forget about the philosophy, because chemists aren't interested in philosophy, they're very practical, and you laugh a little nervously at the charlatanry that inevitably accompanied something like the transformation of gold. Being an alchemist was not a very safe profession. What the alchemists did not realize, but which is obvious, is that if you did make gold from lead, you became an economic asset. And the local ruler of your principality wanted to ensure that the rulers of the neighboring principality did not have that asset. So they imprisoned you in a nice prison where they supplied you with things to make the gold, and when you didn't, this is what happened. To you. So this is a typical fate of many alchemists this is now in Renaissance times. Der nach Urteil und Recht gestrafter Goldmacher, Cayetani, is being hung in this broadside over here. Now, a few things about alchemy that I'll also want to tell you. Well, two more things. I could talk about this another representation. This is an Italian Dutch painting from 1570. Let me just tell you two things about alchemy. One is due to Wendy Doniger's predecessor, the great historian philosopher of religion, Mircea Eliade, the University of Chicago. Here's what Eliade said about alchemy. He said that modern chemists, crying to high heaven that they have nothing in the world to do with alchemy, they're scientists, and the alchemists were charlatans, that they have accomplished absolutely everything the alchemists set out to do, which is to turn lead into gold, dirt into gold. Dirt is what Merck Sharp and Dome starts its synthesis of a new pharmaceutical with. Gold is what we pay for it. And along the way, healing takes place, real healing of people. So it's very interesting. The other thing that I would add to it is this. I think alchemy is an incredibly interesting cultural experiment where a philosophy adopted as science and then was co-opted by it, or as craft, if not a science yet. So the alchemists wanted to do the chemistry to illustrate the transformation. They wound up doing a lot of chemistry. And then, but the other thing that you see here in these images is that alchemy, and that's true to this day, artists love alchemy. So do psychologists. Jung wrote a book about alchemy and psychology. The reason is this transformation aspect has something to do with the transformation of self and the psyche, and it's also so basic in a mythological sense to human culture. What's interesting in the modern context is that you see here the alchemy capturing the artist's imagination. Here we are, modern chemists, and we do incredible transformations, much more interesting and versatile than the alchemists of old. But we lack somehow the hold on the public imagination of ordinary people and of intellectuals that alchemy had in the Renaissance, for instance. What we desperately need is a modern representation of alchemy. Can we get it in postmodern times? I'm not sure, but it's a different comment. Okay, so that was the first definition of chemistry. Chemistry is substances and their transformations, and you can see that my dispersive approach is also to get in the art and the psychology into the story. What happened then? There is now another definition of chemistry, because with very hard work, hot and cold of our minds and hands combined, we have learned what goes on inside substances undergoing transformations. And now, on a microscopic level, we have another image, another picture of chemistry, that chemistry is the art, craft, and business. It'll always remain a business. There is a reason why 70% of PhDs in chemistry go into industry. It's good that there is a business of transformation, and human beings will always be transforming things. Chemistry is now, we now know that inside substances undergoing transformations, there are atoms, and on a microscopic level, and much more interesting than atoms, there are persistent groupings of atoms which rearrange themselves in the course of reaction, called molecules, so that chemistry now on a microscopic level is molecules and their transformations. And these two things, substances and molecules, in the language of chemists, get completely mixed up. They talk about substances, compounds, and they talk about molecules. They think about molecules, they manipulate substances. It's okay that they're mixed up. You just have to, it's in the nature of human beings to mix categories. It is in the nature of, for instance, philosophers to try to unscramble them. It's okay. Here is an example of some molecules. Oh, incidentally, that knowledge came of that there are inside matter, there are atoms and molecules. That knowledge came without waiting for any microscopes to show us what was in there. You can see a lot of good IBM hype about scanning tunneling microscopes that now finally we can see what is inside matter. Where are those scanning tunneling microscopes, which came out in the late 80s, and which showed you in atomistic detail a silicon surface, for instance? Those microscopes could not have been built without the indirect knowledge. That knowledge that we got of atoms and molecules came from our thinking, from our senses, our fallible senses, and the extension of our senses, which are our measuring instruments. And it's a marvelous story of putting together little clues into incontrovertible evidence for those atoms and molecules. A story of knowing without seeing, not waiting for the microscopes. And that knowing without seeing is important to me because it's a bridge to the humanities and the arts, who are masters at knowing without seeing. This is, so here are some pictures of the molecules. Okay, so these are pictures, models, with all the freight that is attached to them being models. Molecules are not olives mounted on toothpicks or marshmallows. They're living, vibrating blobs of electron density moving around. But okay, this is a representation. This is another very interesting thing, but not this talk, about how we represent things in this world, whether it is emotion or matter. But you can see these models of molecules as a tetrahedron with 4 hydrogens named appropriately tetrahedrane, a molecule that's cubane, C8H8, that was made at the University of Chicago by my friend Phil Eaton in 1965, a molecule shaped like a dodecahedron, and finally at the lower right, a molecule that should be on a flag of Brazil, but isn't, and that's Buckminster fullerene, shaped like a soccer ball. These molecules are beautifully simple, simply beautiful, and devilishly hard to make. Just for you in the audience, I'm going to just say something, and then you can think about it, which is because it has something to do with your future. These molecules were made by human beings at a certain time, very definite human beings. I mentioned one. Who made that? Phil Eaton and Tom Cole, who's now University of Atlanta, made cubane in 1965. Each of these was made at a certain time. One of them maybe was in nature, though we didn't know it. That was Buckminster fullerene. But these were made at a certain time. It is an effort to make them which is reflected in the cost of these. If you went out to buy these, you would have to pay a certain number of dollars per gram of these substances. Okay. Today, the easiest of these to make, the least expensive, to the extent that the economics is a reflection of the labor involved, is the latest to have been made. That's Buckminster fullerene. You pay per gram much less for the one that was made the latest than the one that was made before. There's something, and there's a lesson in that hiding. Okay, now the moment I show these to you, the moment I show you these molecules, I feel guilty. So why do I feel guilty? The reason for the feeling comes in that in the word beautifully simple, simply beautiful. That is, these molecules have a direct line into our soul, these representations of these molecules, because they are Platonic polyhedra, because they are so symmetrical. But I know that there are other molecules which are beautiful, maybe more beautiful, which don't look at all like these. Here's one. This is the last time somebody has built a model of a protein. with all 9,500 atoms in it. 4,500 hydrogens, 2,500 carbons, 700 nitrogens, oxygens, 12 sulfurs, and 4 irons. You try to simplify it. You strip away all the hydrogens and a few of the other things, and it still looks like a clump of pasta congealed from primordial soup or a tapeworm quadrille. It is not simple. Its line into my soul is not direct. I had to be taken there by a teacher or forced by a course to appreciate the full beauty of this molecule. This molecule is hemoglobin, the oxygen carrier in our blood. It is the most beautiful molecule I know in the world. And it is not simple. It is not a Platonic polyhedron. So what this is telling me in comparison to this, and where is chemistry? Chemistry is in between these and hemoglobin in complexity, somewhere in between. We can make molecules like all of these. The fact that hemoglobin did not have a direct line into my soul, or I think into your soul. You need to know something about hemoglobin and to build up to it slowly. What it's telling me is not something about hemoglobin. It's telling me about the simplicity of the human mind. That's not what I really want to say. What it's telling me is, I want to say it another way. What it's telling me, I can say it in a number of ways, is that I can say it simply colloquially, we fall for simplicity every time. Okay? I can say it more fancy way. I can say that there are psychobiological reasons why, for evolutionary reasons, we evolved in a way to favor simplicity. Imagine there is a tiger coming through that door. Please don't worry. There's no tiger. But if there were a tiger coming through that door, I've got a lot of sensory inputs in here. Sound, light, whatever it is. I don't have time to process that cognitively. I have 1/10 of a second to start running. Okay, so there is something in our brain which simplifies things, inputs, too many inputs, so that we can act on them. That works at other levels. We have just been through a political campaign. It has been our misfortune to be exposed to, the results were good, but it was our misfortune to have been exposed to too many political ads, I'm afraid, from the good guys. But those political ads, what are political ads? Political ads are the greatest concentration of visual art, poetry, and psychology that money can buy, matched only by a Super Bowl commercial. Okay. For the purpose of convincing poor us that the simplicity of the candidate's position, it doesn't matter which one, matches the desperate longing for simplicity that is in our minds. We fall for it every time. The world is complex. What's being given in political ads is simplicity. Okay, now you think that's political ads, but I tell you that scientists are no better than other people. They fall for simplicity all the time. So for instance, you have physicists telling you that equations must be right because they are simple or beautiful. You have chemists who show you molecules like this, and we think they're beautiful. Let me give you another example from chemistry. We have something in chemistry called we study how a reaction proceeds. We call it the mechanism of a chemical reaction. A mechanism is a specification in a number of elementary steps of how something actually happens. Okay, there happens a chemical reaction, and person A gives you a mechanism for it, so that there are 37 steps in that mechanism. And person B comes and tells you it happens in one fell swoop, in one step. I have made a living out of that. Those of you who know some of my chemistry, you call them concerted reactions. Which one will you like better? Always the simpler one. It's just built into us that we go for simplicity, scientists or not. So what we have to be careful is to give proper place to complexity, and that's part of why I am engaged in this minor tirade, or why I feel guilty about these molecules. Now, the other thing that you see in these is that these are structures. They have a feeling. Okay, so they're not olives and toothpicks, but they can be built, and there is an order in their building. There is something in their building, even when they're as complex as this. And that architectonic sense is interesting because that simplicity or complexity feeling is really, and from a point of view of someone in art or history of art, this is an aesthetic category that makes a human being judge that something is interesting or beautiful. And it's one of the things that we use to evaluate objects. So given that this is an has an architectural feeling to it, even though these molecules are built in very different ways in the flasks in the laboratory than buildings are built, nevertheless, when you move some orders of magnitude upscale, for instance, 12 orders of magnitude, what's the size of this? This is across 5 times, this is across 50 times 10 to the minus 8, 50 angstroms across centimeters, 5 nanometers across. This is the nano object, the ultimate nano object, a protein like this. When you move 12 orders of magnitude, you get to the scale of 100 meters or so. You get to the scale of this building or buildings in general, and what's interesting is that the same kind of feelings or similar feelings about simplicity or complexity enter our minds when we think about whether buildings are beautiful or not. So to give you an example of something where the aesthetic in a building is one which is like that of, in here, of simplicity, not Platonic polyhedra necessarily. I could show you the Parthenon in Greece, but I've chosen a high point of Islamic architecture, the Taj Mahal in India. You see the bilateral symmetry. And you see here that this is the dominant aesthetic. The building may have been complicated to build, but the dominant aesthetic is one of simplicity at work. To contrast that, yeah, this is now we are in Toledo in Spain. This is the Transparente in a cathedral, a high point of Baroque architecture. Look, there are a few straight lines. If you look at right as the altar, the top is an incredible space, a ceiling carved out by the architect with a painting behind it. It's almost hard to see what's happening. There are a few straight lines here, but the general dominant feature of this aesthetic is if any line can be made curved, it will be. And this is the Baroque, the Rococo. Here is, even in the same town, the two contend. This is still also in Toledo in Spain. This is the synagogue, El Transito, a high point actually also of Islamic architecture, but now for a Jewish ritual setting. You can see it here, the simplicity at work in this building. This is just 100 meters from the cathedral. Both of these are contending for, here is just another thing with simplicity. This is a South Indian temple building, and you cannot see on the intricate, this is in Madurai, carving there. Here is another example. This is 100 years old. This is the gatehouse of Park Güell in Barcelona. Antonio Gaudi's, one of Antonio Gaudi's wonderful constructions. This building is not the same no matter what angle you look from. It's different. Now, actually, a little further up in Park Güell is this. So this allows me to get out of this tirade against simplicity. Let's talk, I want to tell you now where beauty resides, or at least one place, and that's true for both the science and for the art, and I can do it around Gaudi's construction. So further up in Park Güell, and I would strongly urge if you go to Barcelona to go there, it's the most life-enhancing structure I know. Up in the park, there's a courtyard which goes off to the right. There are benches, which what you see here, and there's a fall-off, which you see to the left. This was built about 100 years ago. And I want to talk about these benches and the mosaics in them. So there's a choice made by the architect, and there was a choice made by me when I photographed this. And so the line of the benches is not straight. It's curved. But it's orderly curved. The curve repeats, it's not random. So both things are at work. Instead, curved lines are inherently more interesting than straight lines. Scientists try the hell to make straight lines out of everything, but that's silly. Curved lines are much more interesting. I will not go into the psychology of that. But what's interesting is the mosaics. You notice in the mosaics there are some circles and there are some random shapes made. And you and I can imagine another mosaic that could have been done. Black and white square diamond shapes, for instance. How much more interesting, how much more beautiful is this? So why is this more beautiful? It's because, first of all, the combination of colors is pleasing. Good artists do have a way into some emotional color sense, a combination of shapes that is learned and yet intuitive, and that does form a line to our emotions. But the other reason that this is interesting is because we think about it. You know, it's probably not that interesting to a flatworm, but it is interesting to a human being. The reason is that the human being is thinking, why did the artist sometimes use a circle and sometimes use a random pattern? That is, this information is cognitively processed and questions arise. So where does beauty reside? Beauty does not reside in chaos by itself. It does not reside in perfect order or symmetry. It resides at some tense edge where symmetry and asymmetry, when order and chaos contend with each other, fight for a place in our emotions and in our thinking and cognition, both of them. Definition is not that far from what Immanuel Kant would say about this, but this, I think, restores a little bit my tirade against simplicity. Okay, that was the second definition of chemistry. Now let me talk about a third one. So I want to talk about perceptions of chemistry. We do not live by bread alone. People just inherently feel certain things about chemistry. Or instinctively, I mean feel, not inherently. And in a sense, I already gave you part of that story in a Donald Duck cartoon. That's how people feel about chemistry. But now I want to approach it another way, just because it's my way to go around things instead of directly. So imagine that I get asked to testify before the Congress of the United States, and I'm given 10, 15 minutes to tell them what's good about chemistry. It's not going to happen. They don't want to hear what's good about chemistry. They want to hear what one congressman thinks is bad about chemistry in their district, or something like that. But supposing it were to happen. I'm not a politician, but I'm not stupid. I know that the budget of the National Science Foundation has trouble, goes up and down, but the budget of the National Institutes of Health always goes up. So I will choose an example of chemistry that's health-related. I will choose it as close as possible to motherhood and children, because that's what tugs at a congressman's mind. And so it's true, I have this overly simplistic picture of politicians. So I go to a doctor friend and I ask them, tell me something where chemistry has done good for people. So we pull out this slide, which is rather complicated, so let me explain this to you. What is plotted here are the rates of survival on one axis, the vertical axis, percent surviving, of children diagnosed with tumors 5 years after their diagnosis. You have siblings, I have children and grandchildren. Those of us who've dealt with children know that as a first approximation, children are pretty well nigh indestructible. It turns out that after accidents in developed countries, at least, not in underdeveloped countries, but in our country, the second biggest killer of children is tumors. It's not generally known. The tumors of children are different from the tumors of adults. There is a reason why I didn't become a doctor. I don't know what some of these tumors are, and it doesn't, but some of them I do know. What is plotted on the other axis is a time scale with when certain therapies came into effect. Surgery was always there. Radiotherapy, despite Madame Curie, did not become a viable general technique in medicine for treating tumors until World War II and the availability of radioisotopes from atomic bomb and nuclear reactor research. And then 1960, chemotherapy. The brief summary of the story is that until chemotherapy began to be used, nothing worked. And when chemotherapy came on stream, then the survival rates for 6 of the 8 tumors went up to 75 to 95%. And 2 of the tumors are still waiting for someone in the audience to find the right chemotherapy ingredients to use this. What is chemotherapy? Chemotherapy is an exercise in chemical kinetics. It is feeding the body a cocktail of chemicals that kill tumor cells marginally faster than they kill normal cells. If you've known anyone who's had chemotherapy, it's not a pleasant thing to have gone through. It's very difficult. But still it works. Integrated, this is 500,000 children's lives saved by chemotherapy. Chemotherapy is medicine as well as chemistry, but I'll take all the credit for chemistry. Why not? So that's my slide for showing the utility of chemistry. Out of the back door, however, out of the back door of the companies who make the chemotherapy ingredients comes this. Not those companies, because those companies are in public purview, and they don't do such things. It's always someone else who's doing the bad things in this world. Okay, this is not any specific company. This is not any specific side product of that industry. It is a symbol which you recognize as a symbol of the infinity of ways that we have found of fouling our own nest. Standing for ecological environmental pollution. And things have changed. We are very worried about this, and this leads to this two-faced image of chemistry. On Janus here, the Roman god of doors, in a patrician house in Pompeii, you would see this god on a door. And it leads to this image of chemistry, of harm and of benefit, both. And there are a number of things to say about this. Some of my friends in chemistry think that this is a conspiracy by the press, so that the word toxic becomes part of the word chemical. There's no conspiracy. Good news is no news, bad news is good news. The press is the press. It's been that way for thousands of years. It's not going to be any different. I lived for a year, 1960-61, in a country where not a word was said bad about the chemical industry of that company. That was in Soviet Russia, and I don't want to live there again. That's the only conditions under which you get a good press about chemistry. Every chemical, every disaster, every negative thing that you find is an opportunity to learn. With the help of Wikipedia, a professor who sees an article in the New York Times in the morning, God forbid the New York Times should give the structure of the molecule. It never will. If you're lucky, it gives you the name of the molecule. The professor can take that, put up the structure, and can slowly show students by doing this day by day that the molecules that hurt are also the molecules that heal. Here is morphine. Anyone who's had an operation knows what morphine is good for. My God, where would we be with? We wouldn't be there without morphine. Here's the chemical structure, right? Morphine is an addictive chemical. It's easily transformed to another chemical of abuse. Ozone, which protects us from a layer in the atmosphere and from some of the damaging radiation of the ultraviolet. At the surface of the earth, in photochemical smog in Mexico City, destroys lungs and tires. It's not any different morphine that's addictive from the one that's analgesic. It's the same morphine. Okay, it's not the same molecule, but it's the same molecule, the same chemical structure. It takes millions of molecules, many millions to affect this. This harm and benefit, I would say, is actually not so bad, because and then I'll make some psychological comment. It's not so bad because it makes chemistry the truly anthropic science. That is, you know, these molecules, when you go to a doctor and you ask for an antibiotic for your child, you also worry about the side effects. That molecule can heal and it can hurt. That establishes a personal relationship with that molecule. Galaxies and quarks are very nice spiritually, but they can't hurt you or heal you, either one. And so these molecules we care about. I really care about morphine when I have an operation. It's important to me. I think that's one thing. The other comment I'll just make about this hurting and healing, this dichotomy, is this, that I believe that because that I think that people will never feel not ambivalent about chemistry. That's a double negative. People will always feel ambivalent about chemistry. And the reason for it has to do with the fact that chemistry is deeply and fundamentally about change. I mean, morphine does something to you. And the reason we feel, and I think our minds, even though there are different parts of our brain that think about things, it's the same set of neurons that things go down. And I think that there is no way to keep thinking about a molecule and the changes that it occurs, or thinking about a chemical explosion, to keep that apart from what in our psyche we think about change in our lives. Okay, and I think we are ambivalent about change in our lives. Our governments are deathly afraid of change. Well, we just made a change. But they want commerce. They see commerce as an article of progress, and commerce depends on change. But by and large, God forbid one should change the Constitution of the United States, for instance. How do human beings feel about change? Oh, well, those days when I and my children shared a hi-fi system, when they played the same tune 10 times, I wanted to see it changed. With iPods and earbuds, that problem has been removed. Your parents don't have to hear what you play, right? So now, nor do you have to listen to what your roommate is playing. But how do we feel about essential change? How do we feel about changing the country that we live in, changing the profession that we have, changing our partner in a relationship? Not obvious that we want the change. We want it and we don't want it. That's what I mean by the ambivalence. What I'm saying is that that psychic ambivalence about change, which is there inherently in human beings, is going to be reflected in our attitude toward that science which more than any other is about change, which is chemistry. So that people are going to be ambivalent about chemistry. Why did I put this in? Yes, I know. I wanted to make a transition to the title of the lecture as I draw toward an ending, and that is the tensions. So, and I've told you about some tensions. I just talked about one, harm and benefit. Now, what is this? This doesn't look very tense. This was meant to, so these are some plants of the allium family. Can you imagine our world of taste or eating without these plants, without garlic or onions? It's unimaginable. These are great contributions to human society. Are these natural? So the tension I'm talking is of natural, unnatural. So is the garlic plant? Well, yes, a few garlic plants is natural, but 1,000 tons of garlic produced in the state of Illinois is not natural, it's agriculture. Agriculture is a wonderful exercise by which human beings use the natural to do something unnatural, grow 1,000 tons of garlic. So this is another tension. Sometimes it's clear what's unnatural. Sometimes I didn't pick this. There are many tensions. I don't have time to talk about all of them, but there are many tensions in chemistry. I talked about some of them. Let me just mention they're the ones I've put in red here: harm, benefit, natural, unnatural, simple, complex. Every chemical fact is tense because it's positioned on some range of things. It's not one or the other. It's somewhere between simplicity and complexity. And in my mind, incidentally, tension has not quite as much meaning as myth, but almost as much. We don't like tension, but I like tension. That is, we don't like tension in certain ways, but I think tension is life-giving in some ways. Here are some others: creation, discovery. What makes chemistry different is that aspect of synthesis, of making new things. It's in the dominant philosophical principle in chemistry is based on synthesis, on making things, and the logic of making things is rather different than the logic of discovery, which is in some ways more there in some of the other sciences. There are some things here which are not obvious, but I can summarize quickly. What's the tension to reveal or to conceal? Well, when I make some molecule, turns out I don't make molecules, I'm a theoretician. When some of my friends make a molecule, then you have to decide, should they patent it or publish it? That's what I mean. Patenting is very interesting. It's in principle a way of revealing for a license, a royalty, but it is in fact a way of concealing. The most interesting tension is that of identity, of being the same or not the same as something else. But I really want to finish by telling something to you people specifically about, goes into another tension, not obvious that I'm going there, but I think by now you have some idea of my method of proceeding. You've seen me use artistic examples throughout this, as well as science. And in part, I'm living out the fact that I didn't have the courage. I did have the courage to tell my parents that I didn't want to become a doctor, but I didn't have the courage to tell my parents that I wanted to become a historian of art. and you've seen me live out a part of that story here. Art matters to me in various ways, and that's why I introduce these examples, aside from a tendency to want to see the world as one. So this doesn't look like it's heading toward art, but you'll see in a moment. I want to do something else, because I have a feeling I know where some of you are on these things. This is a masterpiece of chemistry. This is not a proper chemistry room, but if you go up in your chemistry lab, in every chemistry lab is hanging a version of Mendeleev's periodic table of the elements. This is its modern form, or one of its modern forms, and it is a masterpiece. And I know, because I was there where you are, that when I saw this, of course it was wonderful as I learned what to use it for, but we are very complicated. In various ways, there was something going through my mind also, subconsciously, and that is, how could I ever do something like this? How could I aspire to create a masterpiece of anything? We always think worse of ourselves than we think of other people. Part of that was, maybe it was just me, but I think it's there. So, in order to find out how it was made, before you come, if you think about it, you need to find out how it was made. So you need to look into history. Now, one of the things that the historians of science have learned is, if you want to find out how something was done, probably the next worst thing you can do about finding out how it was done. What's the worst thing you could do? The worst thing you could do is not look in Wikipedia. The worst thing you could do is to ask the children or the parents of whoever did it how it was done. They'll tell an incredible story. The next worst thing is to ask the person who did it. Because what happens? What happens is Mendeleev did something good. It was recognized as good in his time. He was asked then to give a talk, like I am being asked to give a talk, though I haven't talked about my own work. And he told the story of how it was done. What he said, he had to write a textbook of chemistry in 1857, and he put the 1867, he put the then recently agreed on atomic weights of the elements on playing cards, and he arranged the playing cards both in order of ascending atomic weight, but also grouping elements that were similar in their properties, like iodine, chlorine, bromine, and fluorine, close to each other in some way, and that's how he came upon it. You look in Mendeleev files, well preserved, and you see no playing cards. Okay, so maybe they vanished. But you look in his notebooks, and this is what you see. So this is the first mention in Mendeleev's notebooks of the periodic table. What does he do? At the bottom, he makes, like you would do, if you had to arrange, or if you wanted to arrange some things which had a certain property, atomic weight, in order. We now call it mass, but he called it weight. So you make a list at the bottom of all the things that you have to get in order. And as you get them into order, you cross them out. This is a shopping list, okay? So he did that. He's writing in a mixture of German and Russian because he studied in Germany, and he writes above that, says über. 3 elements didn't fit into the table when he first made it. Mendeleev was acting here as a theoretician. It is in the nature of theoreticians that they make things fit in that don't fit in. He made them fit in. You see the table. The elements, the symbols of the elements were 30 years before agreed on, from about 1835 or so. And except for the missing noble gases, you see, if you rotate this by 90 degrees, you see the modern periodic table there already. And what is the most beautiful thing about this? The most beautiful thing is the crossing out. That's the evidence that this is a human being and not a machine. That it's someone like you and me who makes mistakes and then gets it right somehow, or tries. There is a feeling of human effort conveyed by the crossing out. And you can see why historians of science don't like computers, because what's going to happen in the future to all those drafts, which is what you're seeing here. Now I come to the art. So you see this, and you see that this is work. It's trying to understand. And then human beings are so funny. We romanticize everything that we're faced with. And given this evidence that this takes work, most of us, myself included, still would like to believe at some stage that there is some aspect of human creativity which does not involve perspiration alone, but involves inspiration. And the usual focus of such absurd notions are poets. This is a 19th century image. Gilbert and Sullivan have captured it well, that a poet is a person who does nothing, goes out on a beautiful winter day like this, walks around doing nothing, and then after some time whips out a little notebook, as I always carry, and a pen, and in a fit of inspiration, the poem comes out like Athena out of Zeus's brow, fully formed, a gift from the gods, a gift of inspiration. Let me show you. Here is a well-known poem of the English language. Tiger, tiger, burning bright in the forests of the night, what immortal hand or eye could frame thy fearful symmetry? This is the last draft we have, not the first draft of Blake's poem. He's got the second stanza right. In the first stanza, he's still thinking. He's got a phrase there. I don't have a pointer here, but it's a phrase where it says, could frame now. He has a phrase that he thought initially there, dare grasp. And so it doesn't fit in the first stanza, but he's not going to give up. He makes it fit in here. Tries that, doesn't fit in there. Finally, it finds a place there. I know exactly the feeling in Blake's mind, because what he has done is he's a poet. He's found two words, dread grasp, whose meaning or whose resonances are greater than the literal meanings of those two words. He's going to use that somewhere, someplace. He's going to use that. This is a salvage job. That he's a very high-class salvage job, and it takes nothing away from the inspiration of Blake. Now I put these together. Okay, so they're not the same, art and science. There are very interesting differences which we could talk about, but I find it very encouraging when I see these two things side by side. I see here human beings working, trying desperately to understand some piece of this beautiful and terrible world, and getting some partial understanding, a different understanding in a poem than in a periodic table. But what I feel the humanity of these people, Mendeleev and Blake here, and I feel that I can do it, and that you can do it. Thank you very much.